Hello, I'm Kelly Casey, and I'm just going to do a walkthrough of the code for my notebook for my machine learning assignment 2. So here I'm just importing the libraries I need for the notebook. I'm using TensorFlow and Keras to build the CNN models, NumPy to work with the data, and Matplotlib to display the image of the graphs. I also have just imported the CIFAR10 dataset because this is just the image dataset I'm using for training and testing. Here I'm installing the TensorFlow. There's a little bit of a warning at the end here, but it still worked completely fine. So here in this cell I'm loading this CIFAR dataset using CIFAR10.date load data, and then I'm storing and training the images in labels xtrain and ytrain, and then testing the images and labels in xtrain and ytrain. X test and y test. I then print the shakes back so I can check the dataset has loaded correctly. So here we've got all our numbers. So this just means there's 50,000 training images and 10,000 testing images. Each image is 32 by 32 pixels and 3 means. Each image has red, green and blue colour channels. So in this cell I'm just creating the class names for the CIFAR10 dataset. There are 10 categories for the model. We'll predict aeroplane, automobile, bird, cat, deer, dog, frog, horse, ship and truck. And then I'm just using Matplotlib to display the few images from the trainer set. So this is just showing a 3x3 grid of the sample images before training the model. So here I'm just normalizing the data by dividing xtrain and xtest by 255. So you just want to do this because the image pixels normally range from 0 to 255, but neural networks usually train better when the values are scaled between 0 and 1. And then I just got it to print here. So it's just confirming that the normalization has worked correctly. Here I'm building the baseline CNN model. I'm using Conv 2D layers to detect image features, max pooling layers to reduce the image, and a flattening layer to reduce maps into one vector, and then dense layers to classify the images into one of the 10 CIFAR10 data classes. Then the output just shows here the summary. So here are all our numbers that we've got, all the parameters, the flattening layer, the densing layer, the pooling layer. Overall, the baseline model has 167,562 trainable parameters. These are the values and models the model learns to update during the training. So in this cell, I'm now compiling the baseline model using model compile. I'm using the Adam optimizer to update the model weights, sparse categorically constant cross entropy as the loss function, because this is a multi-class classification problem, and the accuracy and as the metric, so I can measure how many images the model predicts. And then so this just shows there's a little bit of a warning again. It's just showing that the GPU support is not available, so it's just using my CPU instead, so that's fine. So in this cell I'm training the baseline CNN model using ModelFit. So I'll be passing the xtrain and the ytrain as a training data, setting in epochs and using validation data. So the model is tested on unseen data after each epoch. The output here then showing that the training results for 10 epochs. In epochs 1, the training accuracy is 0.4716 or 47.16%, and the validation is 56.49%. By the time it reaches epoch 10, the training accuracy increases to 79.09%, and the validation accuracy reaches 69.99%. So the training loss drops from 1.4704 to 0.6015, which shows the model is learning. So the validation loss finishes at 0.9124 because the training accuracy is higher than the validation accuracy. So it's just showing, it just suggests the model is starting to slightly overfit here. So here I'm just using Matplotlib to plot the baselines, models, training accuracy and validation accuracy. Yeah, so the output here shows the graph, and its training accuracy rises steadily towards and around 79%, while the validation accuracy levels at around 70 here. So it's just showing that the model is learning and the training data better than the unseen validation data. So here I'm plotting the baselines model, training loss and validation loss. And here again, the output graph shows the training loss going down, which means the model is improving on training data. The validation loss is less stable later on, which can suggest a slight overfitting. So yeah, in this cell I'm evaluating the trained baseline model using model.evaluate on X test and Y test. So this just checking how well the model performs on unseen data. And then the test accuracy is a very long number, 0.69989999714, blah, 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 blah. And the test loss is 0.912407, continuing. So the baseline model accuracy correctly classifies 69.99% of the test images. So yeah, I'm just using model predict test to make predictions on the test images. The output here is just showing that the prediction probabilities for the first test image, the high value is 9.16, which is higher than that, but it's about 91.64%. The highest value of the cat is for the cat class, so the baseline model is very confident with the first test image as a cat. So in this cell, I'm using NP-RMAX to convert the prediction possibilities into class numbers. This means that the model chooses the class with the highest probability for each image, and then it's flattening Y-test, so the true labels are clearer to compare the predict. Yeah, so here I'm just creating the confusion matrix, comparing the true labels against the predicted labels, and then using Seaborn's heat map to display it visually. Here the output shows where the model predicted correctly and where it made mistakes. The diagonal numbers show the correct predictions, and the numbers away from the diagonal shows which classes the model was confused about. And then in this one I'm just displaying the first test image using plt.imshow. So I'm just using the predicted class and true class to show the prediction label and accuracy label in the title, and the output here just shows the image with the model's prediction and real answer, so I can visually check if the prediction makes sense. Sorry, I just had to pause that. So if this looks a bit funny, that's because I'm in a house full of children, and my husband's and partner, well, I have one partner, not a husband and a partner, but they're loud. Okay, so so from South 20 we was at, wasn't we? So I'm just importing the classification report to get a more detailed evaluation of the baseline CNN. The output shows position, recall, F1 score and support for each class. The overall accuracy is 0.72, so that's 70%, and the strongest classes include automobile with an F1 score of 0.81 and the ship with an F score of 0.80. The weakest class is the cat with an F score of 0.54, so the model found the cat's harder to classify correctly. Each class has a support value of 1,000, meaning there are 1,000 test images for each category. So here I'm just building the dropout CNN model. I'm using the same general CNN structure as the baseline model, but I'm adding dropout layers after the pulled in layers and the dense layers. So like the dropout randomly switches off some neurons during training, which helps stop the model from relying too heavily on certain features. And here, yeah, so it's just the model summary again. We've got the pull and the dropout, the flattening, the dense, blah, all of that stuff. So it still has 167,562 trainable parameters, the same as the baseline model. The dropout layers have 0 parameters because they don't learn weights, they just help to reduce overfitting. In this cell, I'm just compiling the dropout CNN model. I'm using the same settings again as the baseline model. This just keeps the comparison fair. So in this cell, I'm training the dropout CNN using model dropout.fit. I'm passing the X train and the Y train using 50 epochs and using X test and Y test as validation data. And so start the first one. The output shows that each epoch one, the training accuracy starts at 0.3560 or 35.60%, and the validation accuracy is 0.5289, which is 52.89%. By epoch 15, the training accuracy reaches 63.43%, and the validation accuracy reaches 69.78%. So the training loss drops from 1.7406 to 1.0354, and the validation drops from 1.3741 to 0.8747. So comparing it with the baseline model, the dropout model has a lower training accuracy, but that's expected because of the dropout making the training harder. And the validation accuracy is almost the same as baseline, and the validation loss is slightly lower, which suggests the dropout is actually happening with the overfitting though. I'm just plotting the training accuracy and validation accuracy using MATLib again with the graph. So it's just showing the accuracy finishing close up to 70%, while the training accuracy stays around 63%. Compared with the baseline model, the gap behaves differently because the dropout prevents the model from memorizing the data strongly. And then, this is the dropout model loss. And this output is just showing the validation loss improving overall and finishing at 0.8747. This is lower than the baseline model's test of 0.9124. So even though the accuracy is similar, the dropout model is slightly more controlled. So here we just, I'm evaluating the dropout CNN using model dropout evaluate on the tester data. This is just showing the dropout model correctly classifies about 69.78% of the test images, compared with the accuracy of the baseline accuracy, of 69.99%. The dropout model is very similar, but it's a loss, so it's lower, which suggests it's making slightly more stable predictions. So here I am using model dropout.predict to generate predictions from the dropout model. And here it's just showing that the prediction probabilities for the first test image, the highest value is 0.6481003, which is 64.81%, and it's for the cat class. And then the baseline model, which was about 91.64% confident. The dropout model is less confident, but it still predicts the same class. So I'm just using NP argmax to convert the dropout model's prediction probabilities into class labels, and then create the confusion matrix using the display in Seaborn's heat map again. So this is it's just showing that the dropout model is correct. And incorrect predictions. This allows me to compare where the model makes mistakes compared to the baseline CNN. And so in this one I'm creating the classification report to evaluate the CNN in more detail. The output shows an overall accuracy of 0.70, which is about the same as the baseline model. And the strongest classes are automobiles, mobile, I can't say that properly, with an F1 score of 0.84, truck, and 0.80, and a ship of 0.80. And again, the weakest class is the cat with an F score of 0.49. So comparing with the baseline, dropout improves some classes like automobile, but the cat is still difficult for the model. And here again, I'm just displaying the first test images using PLT ImShow. This time I'm using the dropout model's prediction class label and comparing it with the true label. The output shows again that the label it's predicting a cat when it's actually a cat. So that's great. So here I'm now, I'm building the deeper CNN model using sequential again. So this is one using more convolutional layers. Sorry, I'm not very good at saying that word. It messes up in my tongue. Then the previous models, it has 2 conv-d layers before the first pooling layer and another 2 layers after the second pooling layer. I've also used a larger dense layer with 128 neurons instead of 64. And here the output shows the model summary again. The first layer has 896 parameters, the second layer has 9,248, the third 18,496, and the fourth is 36,928. The dense layer has 244,928, and the final output layer is 1,290. So overall, the deeper model has 271,786 trainable parameters compared to the baseline and dropout models, which had 167 parameters. This model is it's much larger and more complex. So here I'm just compiling the deeper CNN using model decompile. I'm using the same as before. The Adam optimizer, sparse catechol cross entropy loss, and accuracy as the metrics again. So I'm trying to keep everything consistent and fair. So yeah, in this I'm just training the deeper CNN using the model deep fit again. I'm training X train and Y train for 15 epochs and using X test and Y test as validation data. And yeah, so as you can see, the output shows that epoch 1, the training accuracy is 0.4816, so it's 48.16%. The validation accuracy is 59.55%. By epoch 15, the training accuracy reaches 93.91%, but the validation accuracy again is only 72.16%. The training loss drops a lot from 1.4359 to 0.165, but the validation loss increases to 1.3907. So compared with the other models, the deeper CNN learns that the training data is much more strongly, but the large gap between the training and validation actually shows stronger overfitting. So here again, I'm just creating the model like this, model accuracy, just using the same as earlier. The output graph shows the training accuracy rising very high, reaching over 93%, while the validation accuracy stays around lower, which is about 70%. So compared with the early models, the graph shows a clearer sign of overfitting because the training performance is much better than the validation performance. And then I'm doing the deeper learning CNN model loss, again just the same as the other two. So it's showing that the training loss continuing to decrease, but the validation loss increases later in training. So compared with the baseline and dropout models, this is a stronger warning sign because the deeper CNN is improving on the data, but generalizing as well to unseen data. So here I'm evaluating the deeper CNN using model deep evaluate on the data set. The output showing the deeper CNN test accuracy 0.72.599. Yeah, long number. And the loss is 1.306657, and yeah, carrying on with that number. This means the deeper model correctly classifies, so it's about 72.16% of the test images. Compared to, it was a lot better than the other ones because the baseline model was 69.99 and the dropout model was 69.78. So the deeper CNN has a higher accuracy. However, the test loss is much higher, which means more overconfident when it gets predictions wrong. Not great. So in this cell, I'm now using model deep predict to generate predictions from the deeper CNN. The output shows the prediction probabilities for the test images. The higher value is 9.829, which is about 98.30%. for the cat class compared to the baseline dropout models, the deeper CNN has more confidence on this example. It predicts the cat correctly, but with very high confidence also matches overfitting seen earlier. Here I am using NP argmax again to convert the deeper CNN prediction probability into predicted label class. Then using the same thing to create the confusion matrix. So here it's just showing the deeper models correct and incorrect predictions. This helps compare whether the extra 10 layers improve classification across the 10 CIFAR 10 classes. In this cell, I'm just creating a classification of report to evaluate the deeper CNN model. And yeah, so again, the output shows an overall accuracy of 0.72, so this is slightly higher than baseline and dropout. The strongest class are automobile with F1 score of 0.85, ship with 0.83, and truck with 0.83. The weakest class again is the cat with an F1 score of 0.51. Dog also remains difficult with a F1 score of 0.62. So comparing that with the previous models, the deeper CNN gives best overall accuracy, but is struggling with the similar classes like the cats and dogs, which kind of makes sense. Here again, I'm just displaying a test image again using PLT-show. So it's just showing the deeper CNN predicted label and the actual label of the title, so I can visually check the final model's prediction. The output shows that it's correct again. It's like predicted cat and it's an actual cat. I can understand why I would get confused about that being a dog though. Overall, the deeper CNN achieved the best accuracy and of about 72.16. So in terms of accuracy, it's the best model. However, it also showed the strongest overfitting because the training accuracy reached 93.91, while the validation accuracy only reached 72.16, and the test loss was high at 1.3907. So the deeper CNN performed better accuracy, but the dropout model was more controlled because it had the lowest test of 0.8747. So thank you for listening to that. That was the end of it.